Welcome back, Dr. Mandis here. Today I want to talk with you more about the electrons. Last time, in the latest video, we developed atomic orbital diagrams and left it off basically with the slide that you're seeing right there. We got the Bohr model on the left with those concentric rings of energy levels. And on the right, we zoomed in and broke down the energy levels. We basically did a little slice of them and then broke them down from energy level to sublevel into those little blanks there, which are the orbitals. Orbitals, as you recall, they hold up to 2 electrons. Okay, they literally are a part of that sphere that is the electron cloud where 2 electrons roam around. Well, they can also be empty, which is why we say up to 2 electrons. Alrighty. Before we start placing electrons on there and saying something like, I have 2 electrons in the 1s, 1 electron in the 2s, stuff like that, I'd like to do just a little bit of analogy with you because what we're going to do is look at this. All right. What I have here is a basement apartment. Down here is an apartment, you know, and I got our Martian dude hanging out in the apartment. Okay. And we have our groovy little Smurf guy. I need to change my color. Up here, playing a joke on him, well, mean joke. Basically, he grabbed the fire hose and he's just going to basically fill the steps with water. Cool. So if water comes on here and fills the steps, it should inundate this step first, don't you think? This step will fill up, and then it'll go to the second one. That makes sense, right? Water runs downhill. Lower energy states are preferred. So the water runs to the lowest energy state by potential energy. Same gig for the electrons in the energy level diagram. If you have, say, just 2 bits of the energy level diagram, what? I'm confused. All I'm saying is we're taking this little bit of the energy level diagram. Okay, if you take that little bit and place 3 electrons in it, will the electrons go 1, 2, and then 1 up there? Or will the electrons pair up first and then put 1 there? Remember, the orbital, the blank, is an orbital and it holds up to 2 electrons. It should fill first. This is a diagram of energy, increasing energy. Lowest energy is going to fill first. Once that's full, it moves up. Just like within the steps, once this step's full, this one fills up. This one doesn't fill up magically on its own first, okay? Lowest energy fills first. Just makes sense. This beautiful little thing is called the off-bow principle. All right. Next, what if you got more than one? You got a room in like the 2p orbital, 2p sublevels, and we want to put in 2 electrons. Do we put like 1 in the 2s, 1 in the 2p, put them together? I already said that's correct. Okay. What if you have this is full, you got to put in 2. Should they pair up or spread out? Okay. Well, go back to the steps. When it starts to inundate this third step, is it going to pile up here first, then pile up here, or is it going to just spread out? The water is going to spread out. The electrons are going to spread out. Electrons are what charge? Negative. You think really that you're going to bring those 2 negative electrons together without costing a little bit of energy? They're negative. They should repulse each other. To bring them together and pair them up, that takes energy. So no, that doesn't happen. They spread out. Okay, when they spread out, here's something that may not be intuitively obvious. They have to spread out not with opposite spins, but with the same spin. If they're opposite spins, they'll end up pairing up, and that's going to cost you energy, so that doesn't happen. This thing is called Hund's rule of multiplicity. Basically, put in the electrons from the bottom up, okay, spread them out. If you got yourself a choice to pair up or spread out, pair them up. Okay, if you don't have a choice, like say for instance, you have 3 in there, the fourth one's naturally going to go in here, and we'll see that in a second. But we got one more gig to say. Okay, in the energy level diagrams, we have a pair of electrons. Opposites are the pairs. Okay, electrons spin. They spin on, easiest way to think of it is them spinning on an axis. One clockwise, one counterclockwise, or clockwise, counterclockwise. They spin in opposite directions. One is called spin up. One is called spin down. Which is which really doesn't matter because all you do is take your computer screen now and flip it and ups become downs. But the gig is to make a pair, you need some sort of oppositeness. Not really a word, but I dig it. You need some sort of oppositeness to attract them together because opposites attract, likes repel. Like spins would repel each other, so to speak. And so the only way you're going to overcome that negative charge repulsion is to pair them with the opposite spins. Okay, Pauli exclusions say use opposite spins. And to be technical with you, what you would really say in a Pauli exclusion, to put identical electrons in an orbital makes really two electrons in the exact same point in space, which can't happen. Okay, but for first year chemistry, it's kind of hard to visualize that, but Pauli exclusion just says use a pair in an orbital. Alrighty, so we ended up with a periodic table that looked really gruesome like that last time we talked, so we'll have to break that out again. And basically, I just want to do some examples. We'll do 3 examples and call it a night. But we have the energy level diagram for phosphorus. For all of them, draw the blank energy level diagram, then add the electrons. It's kind of like playing a game of Monopoly or something like that. Don't set up the board while you're playing. Set up the board, then play the game. So every time you're going to set up the board and draw your blank energy level diagram, this gig, draw the blank diagram first. You don't have to draw all of it, draw as much as you need, but draw the blank diagram first, then put the electrons on. It's a lot easier. Okay, a lot easier. Okay, so let's look here, draw the energy level diagram for phosphorus. Phosphorus is way down here in the periodic table, 3rd row. Remember, you got helium would be right here. We got 1, 2, 3 rows. So of those energy level diagrams, we're going to draw 3 complete rows. 1, 2, 3. Label it energy, label it phosphorus. This is the 1s, 2s, 2p, 3s, 3p. All right, much like in Monopoly, start at go and roll on, okay? Or in Sorry, start at your home and move out. Every time we play this, we're going to start here and move along until we get to our element right there. Another way and so we put in 1 electron for every element we pass till we get to phosphorus. The other way to look at it is phosphorus is in the 3p, okay? Down here, this is the p sublevel, this is the s, this is the d. So phosphorus is in the 3p. So he's the 3rd one of the 3p, so we're going to end up with an energy level diagram with 1, 2, 3 electrons in the 3p. Everything else before it's going to be full. So we put in 1 for H, 1 for He up here, 1 for Li, 1 for Be, 1 for boron, carbon, nitrogen, bang, bang, boom. Now we're full. Put in oxygen, fluorine, neon. We're at the end of the 2. Come down here, you start the 2s, Na and Mg. We drew border lines when you drew your diagram. We had these little line here. So we're going to do these 2 first. That's the 2s. So put your 2 electrons in the 2s. 1, 2. Then jump over into the 3p, I should say. 3s. In the 3p, we're going to have aluminum, silicon, and phosphorus. So we put in aluminum, silicon, phosphorus. I know you just got to rep that a few times, just like playing any new computer game, something like that. Once you play it a few times, you know where all the moves, you know the controllers and all that. So let's play it again. This time we have oxide. I know it's charged. Ignore that. Oxygen is right here on the periodic table. Already. Oxygen is in the 2nd row. Remember, this is the row 1 and 2. This is S. This is P. This is T. So draw an energy level diagram. Instead of 3 complete levels, we're only going to draw 2. 1, 2. 1s, 2s, 2p. How do you know that there are 3 orbitals in the 2p? Because in the p's, there are 6 elements. 6 elements, 6 electrons, 6 elements, 6 electrons. Divide by 2, we get 3 pairs. 3 sets of 2, 3 orbitals, because an orbital holds up to 2. So anyway, oxygen is down here, the 4th one in the 2p. So H and He are going to go in. Li and Be. And then we're going to put in B, C, N, and O. So we're going to put in B, C, N, and O. We paired up because we ran out of space, and we know we're stuck in the 2p because that's where we are. So the 4th one goes in the 2p. Cool? Some students have questions of how do I know that it's 4, not 3, stopping before oxygen? It's kind of like in a Monopoly. If you're rolling to get on Pennsylvania Avenue, you count Pennsylvania Avenue as one of the numbers you got to land on. Okay? There are 4 it's the fourth one in the 2p. 1, 2, 3, 4. So put 4 in the 2p. One more, aluminum. Let's do the aluminum cation. Okay. Oh, messed up that. Forgot about the oxide. It's a 2 negative up there. I forgot about that. Thanks for reminding me, guys. It's an oxide. It's 2 negative. What does a 2 negative mean? Well, earlier you should have learned, 2 negative means 2 extra electrons. To be negative, you gain electrons, so gain 2 more. Either think of it this way, I'm going down 2 more to be at neon, so I'm 2 more in the 2p. Or you look here and say, hey, I need 2 more. They can go right here. 1, 2. That's it. Easy enough. Okay. As far as the aluminum goes, aluminum is here, down here in the 3p. So much like for phosphorus, we're going to draw 3 complete energy levels. Alrighty? So same energy level diagram, atomic orbital diagram you drew for phosphorus. First row, second row, just like we did for O. 1s, 2s, 2p. And the third row of the table looks just like the second with an S and a P. So you got the S, 3s, and 3p. Cool. Make sure the 3p is slightly higher in energy than the 3s. Okay, not as you get a much bigger energy difference here than you do here. That would be really good. Okay. Anyway, put in your electrons, starting at H, 1 electron for every element to get to Al. Al is going to be the first one of the 3p's. We're going to put 2 in the 1s, 2 in the 2s, 1, 2, 3, 4, 5, 6. Put them up singly, then pair them up. Then you have 2 in the 3s and 1 in the 3p. Alrighty? Aluminum is a 3 positive. Well, for a 3 positive, you lose 3 electrons. Which 3 electrons? The last 3 you put in. So you lose 1, 2, 3. I would just cross them off to say, hey, those were lost. Alrighty? Up here, you would look and say, hey, I got rid of aluminum, magnesium, and sodium. Cool? And if you notice, the aluminum cation is identical to the oxide. Where'd it go? The oxide. 2s, 1s, 2s, 2p are full. 1s, 2s, 2p are full. That's important, and we're going to get to that in our next one. But really fast, let me just say this to you. There's a thing called electron configuration. See all the stuff in black I got written there? Let's write it again. 1s, I should write it in black to match. 1s, 2s, 2p. The things in red are the electrons. We got 2 here, 2 there, 6 there. That's called an electron configuration. I'll talk more about that later, but all this electron configuration is just like a shorthand of the atomic orbital diagram. Alrighty? I know I went over this kind of fast, but as you practice it, trust me, it becomes really easy. And it's really, really, really useful. You have to, if you know this, you can understand bonding, you can understand charge formation. A lot of the next few units of chemistry make a lot of sense because you know where the electrons most likely are. Alrighty, I'm Dr. Mandis. You guys take care and have a great day. I hope you like it. Take care.